Okay, so we're just gonna do a recap from the in this video we're going to be welcome to this video. Welcome to the second video of this series. And this might be the last actually. The turn-up hasn't been so much, so and creating the videos itself is kind of stressful sometimes. So maybe I'll just maybe we won't continue to fight. Okay, but so from the last video we talked about the Xor Neural Network. Yeah, so the Xor Neural Network just is a just the simplest version of the neural network. You have an input layer with 2 neurons, and simplest case a hidden layer with 2 neurons and an output layer with just 1 neuron. Okay, so and we written a code for that in C++, so we're going to be creating a JavaScript version of it. Okay, so I'm going to explain everything I am doing from how we created this code exactly from scratch, and we're going to test at the end of the video. Okay, so please you probably have to pay attention to how everything goes so that you can understand how it's happening, because it can be confusing sometimes. It can be really confusing. Even just implementing something as simple as this can be really confusing. Okay, so let's start now. Alright, so we're going to be just like converting the code, we're not like building it. So first we're going to do is define our constants here. Not constants, we'll just say the input should be equal to 2, and say const hidden neuron should be equal to 2. That's 2 neurons. Or define the neurons in each hidden layer, and output neurons should be equal to 1. And then define our learning rate. Learning rate should be equal to 0.1. Okay. Now we've done this part. The next part is this. So this is just a JavaScript C++ representation of a JavaScript object. So we can just assign the object to say const neural net should be equal to an object, and we're going to say the input layer are going to be arrays of arrays. So they're going to arrays of doubles. So we just call them arrays of numbers. Okay, well, don't worry. So to say the input layer, what this means is that it's going to be an array. That's what the vector means. It's just an array, JavaScript array that just contains some numbers. Okay, so then the hidden layer is going to be the same thing, put some numbers. Since it's just 1, this is just a hard-coded version. Okay, and then the output layer is going to be an array, of course. So, okay, so now we've done this part, and let's define our activation functions. Now, as we said, if you remember, we said activation functions are what brings non-linearity into the neural network. Else, you just have a regression model. So, a neural network without an activation function is just as good as a regression model. Just like the ones that, okay, like the simplest version of a regression model is like addition. You have to be the neural network and add 2 numbers together. That's a regression model. It's a linear problem. Okay, so these are non-linear activation functions, but we don't even need most of them. We just probably need a few of them. But let's just model them. So these are just functions that returns certain double, that's a number, a decimal number, because our values are going to be decimal. The results. Okay. So we're going to call a function here. We call functions for all this one. So function sigmoid. So it takes in a number, just call it a number, so n, and what it does on the number is that it's going to return 1 divided by 1 plus, this is the formula for it. It's actually a formula, the activation function. So it takes in the sum of all the weight and the values of the neurons coming from the input layer, and then passes it. That's what n represents. Pass it into this function here. Okay, so we're going to call it math.exp exponential. going to pass in minus n into it, and that's it. Okay, that's it. Yeah. Let's wrap this up. Let's open the wrapping initial. This is just what we get for the sigmoid. So let's do it for the ReLU. ReLU is just very simple. It's just a condition saying that if the value of that neuron is less than 0, then we should return it as 0. Else, it should be whatever it is. So we're going to using. You can even just copy this. Still the same syntax. So just going to return this. So if n is greater than 0, then return n, else return 0. So anything equal to or less than 0 should be 0. Okay, that's for the ReLU. And the ReLU is actually like one of the most very active acquisition function. Like when you use ReLU, it actually makes your neural function really fast. Okay, and the last one is hyperterm. Let's not do hyperterm because we're not going to use it. So let's get the derivative. So doing the backpropagation, just the same way you're passing your values through your acquisition function, you have to pass them through the derivative of the acquisition function. So that's where chain rule comes in. And the formula applies. It's a mathematical complexity somehow, but we're not going to go into that. Let's just model the formula. So the sigmoid has the derivative of sigmoid. We're going to take in the value of n, and it's going to return n. This is the derivative of sigmoid 1 minus n. So if you're curious, you can actually find the derivative of this with respect to n. Most likely you might get something similar to them. So function the ReLU. So ReLU takes in n. Let me just capitalize this one. So use common case. Okay, so the ReLU, it's this as well. We can just copy the code. So what it does is that if n is greater than 0, then 1. It's actually just like the same thing, right? Okay, no. If n is greater than 0, instead of returning n, it returns just 1. Else returns 0. So that's the derivative of ReLU. So instead of, in this case, where we're doing the actual activation function, we're returning n if it's greater than 0. Okay, we're going to return 1. So this is the formula. Okay. Alright, good. So next thing, let's define our training data. So const, this is an array of an array. Training data should be equal to, so we're gonna have 0, 1, it's 0, 0. So these are our training data. Okay. So then const. Okay, let's define this as, okay, these are our input, training data input. So we want to now put the expected output that we're going to use to train the neural network. So const training data output. So it's going to take the output for this one. We need it to be 0. Okay. So this one is going to be 1, 1, 0. So when we have 1 and 1, we expect 0. When we have 1 and 0, we expect 1. So this is it. This is our training sample data. So now we're going to create a reshuffle algorithm. Reshuffle algorithm is actually to ensure that the neural network trains faster and more efficient. We have to reshuffle the data set so that it's not like in the exact same order. Okay. In most cases, this might not be really, since we're doing a very simple case, we might not really need it. But let's just try to implement it. Okay. So the function, we're going to call it reshuffle training order. My type reshuffle training order is going to take a value, which this is actually an array. Okay, it's going to take an array. So okay, just passing array here. So in this case, with C++, we're passing it by a reference, so we're going to directly update the training order. But for JavaScript, it might not really update it, except we declare it globally. So let's just say we're going to declare the training order globally. Okay, so we have to pass it as a as a parameter or argument. So we're going to say training order is going to be equal to say 0, 1, 2, 3. So the training order, just what it does, you see that it actually it has these values, 4 of them, okay, and this 0 represents the first value. You know, in programming we use 0 indexing. So 0, 1, 2, 3. It just tells us how we're going to actually match, like, okay, how we're going to put in how we're going to train the neural network, which data set are going to use at a particular time. So sometimes when we reshuffle, this might become 2, this might become 1. So sorry, this might become 3, this might become 1. So it's just going to shuffle the way it's going to accept train, like taking the inputs. So it's not going to be in a fixed order, just to speed up training and ensure generalization. Okay, so let's write our reshuffle algorithm. So since we declared our training order as a global variable, first we're going to generate a random number. So we say const random should be equal to math.round. So let's round up the number. We want to generate a random number dot random. So we're going to now tell it that we want this random number to be between the range of 0 and I plus 1. That's what this code means actually. So why are we saying 0 and 1? I plus 1. We just want to generate a random number. So what it does now, let me explain this code. So this generates a random number. Let's say I is actually 0, then it's going to generate a random number between what 0 and I plus 1, which is 1. Okay, and then let's say the random number that was generated is 1. So we now store the value of that 1, which when we now say training order at index 1 is going to give us 1 here. Okay, we're going to store it here, and then we're going to now set that what then, okay, at index I, which is 0, so it's going to be 0. Okay, so then the random number we generated, remember it was actually an index of 1. So when we pass that index 1 here, it's going to still give us 1. According to this, it's still going to give us 1. So we're now going to assign that's not going to be the new value of I, index I. So we're just saying that the value, the array value of the random number should be the array value of index I, and then we're going to say the array value of that random number. Like, you know, we're going to interswitch them. So that's why we actually save this in temp here. Index I, we save this in a temporary variable, and then we now assign the value of index I to be the value of the random, and then the value of the random to be the value of index I, which we save in temp. Okay, so that's what we're going to do. So we're going to say temp should now be equal to training order index I. Then we're going to say training order index I should be equal to training order index random. Now we had to do this math.round so that, because you know it returns in decimal, so we had to convert it to random, to a whole number. Okay, so as we go and say training order index random should be equal to temp. Okay, I've written our shuffle algorithm. Alright, next thing we want to now do, okay, this one is not actually necessary. This is not necessary. Let's forget that one. So we're going to create our layers and our weight mesh. So now there are a lot of ways to do this. There are a lot of ways to do it. For example, when I first created the neural network, what I did was that I assigned these neurons as objects which had properties which tells us the weight that's actually coming out of it and the weight is entering into it. But that might be inefficient. The reason is because the same weight that's coming out of this guy is actually the same weight that's entering this guy. So how do you want to take account of all those things now? Because then it kind of seems like they're creating duplicates of them on one side for each neuron. Say a neuron, because it has an input to it, obviously it has output to it, and those output weights is actually like the same weight that's actually entering on that neuron. So if you now initialize some values for this guy's output weight. What about this guy input weight? It should be the exact same thing. So I thought of a different way to do it. Why don't we just consider this whole layer like this as a layer, as a mesh, right? A mesh of weights. So in computer neural networks, this is going to, like, you see there'll be a lot of weights here, so it's going to be like a mesh. That's what I call it, a mesh. So we have to create an array to store this mesh, and this array is going to be based on how many inputs we have here, how many outputs. That's how we're going to create it. Okay. I don't know if you understand what I'm trying to say, but okay, for each input neuron, we're going to create a weight for every output neuron. Okay. Same thing we're going to do for each of these inputs. This is a hidden layer. So for each of these neurons, we're going to create a weight for every output. There are 2 here. We're going to create a weight for 2, and then just like for this one, just like a matrix, right? For this one, just like a row. I'll explain. Okay, let's just take, for example, let's just do something like this now, and then we have values 0, 1, 2, 3. Okay, and okay, let's do it like this. So assume this is like a matrix, right? So alright, so something like this now. So let's do it like okay, yeah, for each of this, yeah, 2. So okay, so our first weight mesh is going to look exactly like this. See, for each of these output neuron, which represent this first row, we are creating 2 columns for the 2 neurons in the hidden layer as these values. So these are going to be random values we're going to initialize. Remember, we said we're going to set the weights to be random values. Then we now train it. Then it's going to now be refined. It's going to now refine itself. Okay. And then for this second input neuron, which is this second row, we create individual weights for the 2, either 3 here, then this is going to be 3, have another value. So that's actually what I mean. Okay, so now let's just go back and let's create it. Okay, so sorry. So the first thing we're going to do is create a function. Let's call it create layer weight mesh. Okay, so now this function actually takes a value and it takes a vector of an array, okay, and it returns a value, of course. Okay, so inputs, outputs. Okay, so now remember we said for each input we're going to create all the outputs. Okay, yeah, so let's do that. So first we're going to take in the parameters. First we need an array, vector array. So just call an array here, and then we need a number. So let's say input neurons, and then just call it output neurons. I'll not confuse anyone. Let's just say output. So I already defined the variable called input neurons. Input. So this just represents the number of neurons in the input, the layer. It doesn't necessarily mean the input layer, but the layer that we're coming from, the layer we're mapping to. Okay, so so the first thing is just very easy. We're going to look through creating a for loop. First, let's just create an array. Say const new array should be equal to this. Okay, let's say the array should be equal to this. So we're going to create a for loop. Create I equal to 0. I is going to be less than input. Yes, less than input. I should increment the for loop. Let I equal to 0. Sorry, use J now. J equal to 0. J is going to be less than output, and J should increment. Okay, then we can say new array index I index J should be equal to math.random. So generate random numbers right there. Alright, good. Alright. Okay, I don't think we even need this one. We didn't need this parameter. Sorry. We don't need this. And then we're just gonna tell it to say return new array. So now let's test this. We're gonna test this. Let me just show that it's working. So here's a console.log. We're gonna call in a create weight mesh, passing an input two numeric inputs and two in the output. So let's just run this code. We're going to see the vector of the matrix I was talking about. Oh, we didn't print anything. I didn't print anything. I didn't save it. Okay. Alright. So since we didn't do something right, I just said new array xi should be equal to an array. Okay, good. That's what I was talking about now. So what I did here, we're trying to push in. We just defined the new array the way it was. So this is just as good as saying this is equal to this, right? So it doesn't know that whether each of the row is still an array again. It doesn't actually have an idea about that. But anyways, so we just set the ith index to be equal to an array because it's an array, which is this, which can now hold the rows within it. Okay, so remember, if we continue doing this, it's just going to keep on generating random numbers. That's the goal actually. We should start from random numbers first. Okay, so that one is working. So the next thing we want to now do is to create a bias mesh. Now the bias mesh is very similar to the weight mesh. Remember what I said, for each of these neurons we have a bias which we're going to add up to the sum of the product of the weights and the input neurons. We'll add it up to whatever value we get from this times this times this, sorry, this times this plus this times this. We're going to sum it up to the bias which is going to be here. Okay, but for a very simple implementation you might not really need a bias. I'm just trying to add it so that let's say that we actually added it. It actually makes the training much more faster. Okay, so the function for it says that we taking a side. Okay, sorry, taking an input neuron count. Okay, so we're creating a bias mesh. Remember, we're just creating a bias mesh for per layer, but not actually like, it's not like this width that we're trying to map from an input to an output. No, we're just taking, we're gonna store it per each of this layer. Okay, so it's just a single for loop. I'll just store random numbers into an array, a single array representing each layer. Okay, so let's create a function here. Function create bias mesh, and just takes in a neuron count. Just call it neuron count. As for that layer, any layer I want to create a bias mesh, how many neurons are there? Okay, so just const new array. So, and then create a for loop. So mostly what is needed to for loop. I is going to be less than neuron count. I should increment. So we can now say new array push. You can say that push actually. Just do that to next I. The next I should be equal to math dot round math dot random. Okay, so created the function to create a bias mesh. So all it just does is assign some random numbers to a single array which represents, so it depends on sorry, but when we start using the functions you see we'll explain how we're going to use it. Okay, so the next thing, we don't need this one, and I would not need this one as well. So let's go to the feed forward. Feed forward, as I said, was um, this value here times its width. Okay, let's do it with respect to this one. So what this guy is going to take, we're doing the feed forward. Remember, look at where these arrows are pointing to. So they are actually pointing to the neurons they are mapping to. Okay, so what this is going to come from this line is the weight, which represents the importance of this neuron to this neuron. Okay, so it's going to be a value. That's what we initialize here. That's what we're creating. We're creating a weight mesh, assigning for every input weight, we're assigning an output weight or the output weight. Okay, so it is 2D array, 2-dimensional. Okay, so yeah. So we feed forward now. This times this plus this times this plus our bias. That's feed forward. So let's see how we implement it in the code. Okay. So I was using C++, so I had to do some stuff. So I didn't for each loop here. So it didn't give me manually an iterator, so I had to create one by incrementing the number because I actually needed it. So hold on, we're using iterator here, using it for JavaScript, I and J and K and whatever. Okay, so the first thing we have to map. Now this function actually takes a couple of parameters. The first parameter it takes is layer 1. What does layer 1 mean? Layer 1 actually means the weight mesh. This first weight mesh, I call it layer 1, right? The second parameter it takes is layer 2, which is this second weight mesh, just an array containing weights, containing decimal numbers, let's call it like that. But we are carefully mapping. Remember, I just printed it out for you guys. We're going to be mapping for each input neuron and output neuron. Okay, that is actually how we are doing it. So we have to be careful when we're mapping. So yeah, mapping makes our work easier. We don't have to create objects and start doing dot this, dot that. No, it just makes things easier for us. But we have to be careful to ensure that we map it correctly. Okay, now it takes in the neural network itself, which is this shit that we find here. Yeah, this guy. So we want to be updating the neurons, which of course we said that here. Remember here we created empty arrays. We're going to be storing for each. This is going to hold the neuron values. Okay, and also takes in the order, but we don't have to pass this here. In C++, we have to pass it here. If we didn't define it globally, we have to pass it by reference. But don't worry, let's not go into anything else like that. So let's just. So the first is what we're going to need now. We're going to pass in this. We'll pass in this as the weight mesh for each layer. We're going to now pass in the order, telling the neural network, okay, which training input are you going to be using this time around? Okay, and input data. Come check something. Already passing the training order. Don't worry. Okay, we're just passing the training order and hidden layer. The bias. Okay, this is the bias, and bias will output here. That's all. Not too much. Let's create a function. So function. So this is going to be feed forward. So this is kind of straightforward, but it might be complicated. It might become complicated. We just have to try to follow through so I don't get confused. So my first one is going to be a layer. Let's just call it weight mesh 1. Passing the weight mesh 2. Passing order as this order represents. So we're going to be iterating through each of these numbers. We're going to be reshuffling for each epoch, and then epoch represents how many times you want to train the neural network. So for each of the epoch, we have to train it on all the data sets. Okay, so the training order represents the order. It represents the way we're going to for, like, if this is 1 here, it means we're going to segregate. We're just going to go to training training data set 1, index 1. We have index 0, index 1. Pick up index 1 and they're going to now run it using neural network. Okay, just tell us which one we're going to use. Okay, so this number represents, so we're going to look into each of the numbers here. So that's what this order represents. Tells us which particular order are we at. Are we at the order 1 or 2 or 3? Just tells us which data set that we're supposed to pick to do training this study for this particular round. That's what it means. So next, we now pass in the bias mesh 1. So bias mesh 1, I just call it bias mesh 1, but we can just call it bias of hidden layer. This is the bias of these 2 neurons. Remember, output neurons don't need hidden layer. They don't have, and they don't need hidden layers because they don't really do any sort of computation. They just pass their values forward. Okay, this is where the calculations are, and then we need a bias here as well. So let's just call this one bias of hidden layer. Let's call bias of output layer. Okay. Alright, our parameters has been set. Now the first thing we're going to do is to now assign our input data to the input layer of our neural network. Now we created the neural network up here, neural net. So this is the actual neural net. It has 3 layers. Okay, so let's assign the input values. So I'm going to create a for loop. Okay, just use a for each loop. So let's say training data inputs at order. Okay, dot for each bar. So we can say neural net at, probably let's assign, get the index as well, idx. We can call id or whatever. So idx is going to be equal to val. Okay, and yeah, that's it. So we just assigned our training inputs to our neural network first layer. Sorry, I should just say input layer here. Okay, so the input layer, now assigning properties to it. For the index, assigning values to it. Okay. Alright, so let's continue. So the next thing we want to now do is, okay, so this code says we're looking through each hidden layers. For the hidden layer, each neuron, and you're saying account the net sum, create a net sum. Now look through the input layer and net sum plus equal to layer 1 slash times input layer, blah blah blah. Okay, this might be a little bit confusing, but let's go over what we're actually doing here. But the first thing we have to do, remember from here, what we did here was that, I don't know, let me explain, don't worry. Let's just come here. What we're going to do here, instead of setting this as empty arrays, we want to set them as, we use this method of creating the array, and then we can now pass in the input neuron here. So this is going to resize the array to the exact size, probably is going to initiate everything to be 0. Okay, so that's what we want, because at this point we're going to need to do it straightforward. So new array hidden neurons, and lastly new array output neurons, and let's just constant log this to see. Also log neural nets. Okay. Oh jeez, where did this come from? Line 9. Also the lines. New array is not defined. Sorry, okay. That was a mistake. Okay, now this is exactly what I mean. It tells us 2 empty items, so it has created items for us. So we can test that. We can say that input layer dot length. So this should give us 2, because it has 2 empty items. Yeah, good. So we can now iterate through it. Okay, let's remove this. So at this point here, we're going to now take a for loop. We're going to look through for every input neuron. Yeah, correct. I think that's correct. Let's look at this code. Okay, for every neuron in the hidden layer, we're going to look through every neuron in the input layer, and then we're going to do some sort of remapping. Okay, we want to map the exact link that's connecting both neurons together, and that's what we're doing here by getting this index exactly gives us the weight that's mapping that hidden layer neuron to the input neuron. Okay, so let's do that. I don't know if you understand, but just try to look at it very well. Okay, so my laptop is actually hitting like this. Sorry. Okay, let's just continue. So we're gonna create let I equal to 0. I is going to be less than the neural net dot hidden layer dot length, or we could just say the hidden layer. So let's just say the hidden layer. So it's going to be less than hidden neurons. I should increment. So this is going to give us access. It's going to give us access to the number. It's going to give us an iterator that looks through the exact number of neurons in the hidden layer. That's exactly what this code is doing. So we won't need to do this or this because we're already getting the iterator. Okay. So define a new value. Let net value sum be equal to 0 because we're going to be incrementing. Remember we said we are adding up the values that are coming. Okay. So now we're going to look for each input layer now. So for loop, let j be equal to 0. J is going to be less than input neuron, and then j should increment like this. Okay. So we're gonna say net value sum to plus equal to. Now remember, for when we're dealing with the input layer and the hidden layer, we're dealing with mesh 1, with mesh 1. Okay, we're dealing with this mesh here. So this is actually what we're going to consider. Okay. So remember that we said that for each input neuron, we'll be creating, for each of the input neurons here, we're going to be creating a corresponding value for the number of output neurons in the hidden layer. Okay, so that's what we're going to now do. That so it means our first accessor or our first I value should be index j because it represents the input neurons. Then index I, which is now representing for that particular hidden layer. Okay, it's kind of confusing, but just try to look it through. You understand it. So we're going to multiply by the value of that input layer, which is going to say neural. Remember, I've already assigned the values here. So neural net dot input layer index j. Okay. Yeah. So this gives us the value of the input, that particular input neuron. And next thing, out of this loop, so we're going to look through all the input layers that neuron that is connected to. So we're considering this first hidden. So now we're looking through the hidden neurons. So consider first, we're going to consider this input neuron that is connected to. Sorry, and this input neuron that is also connected to, and their values are going to sum up. So that's what we're going to do. We're adding it up to the value as it's defined to 0. And so outside of here, we're going to now say net value sum. So we've already summed everything up together now. We've added the weight times the value of the input neuron. Okay, so now we're going to now add bias plus the bias. So we said the bias hidden layer, because we get that index, particular index of that hidden neuron. Because for each hidden neuron, we're creating a bias. Okay, so index I here. And lastly, we now pass it through our activation function. So it's kind of straightforward actually. So wait now said the let's not wait now reassign the value of that, or actually reassigning modifying its value. Okay. So wait now say the value of that particular hidden layer. Wait now say neural net dot hidden layer index I. Yeah. So this presents that particular hidden neuron. Should now be equal to sigmoid. Let's just use sigmoid in this case. Sigmoid, I'm passing the net value sum. Okay, let's review it. Hope I'm not making a mistake. Neural net dot hidden layer is a neural network itself, and getting index I, the particular hidden layer we want to update, and passing sigmoid. And finished. Now, before we wrap up the feed forward, we have to do for the output layer as well. Remember, we just finished, we've done feed forward for this, so I've covered everything that comes from here. We've done our activation. Now we have to do for this one, anything that comes from here. I'll wait down, do the feed forward for it, passing activation as well. Okay, so let's do that. So for loop, very similar. I equals 0, I is going to be less than output neurons. I should increment, then and then we're going to now instead of having input neurons here, we're going to have this. So the input of the output layer is actually the hidden layer, or the last hidden layer. So remember I said that it can be in a much more complicated version. It could be more than one hidden layer. So we just know that the output layer is mapping exactly to the very last hidden layer. Okay, but in this case we have only one, so I just use it the way it is. Okay. So we're going to just the same way we did here, define the net sum, net value sum equal to 0. That's just the temporary value is going to hold all the contents coming to that input output layer before we now sum it up and then add the activation and then we assign it to the neuron itself. Okay, so looping for let j equal to 0, j is going to be less than hidden neuron, and j should increment, and then next it will say net value sum should now plus equal to, now wait and do weight mesh 2 now. I didn't spell this thing correct. Let's just leave it like that. Increment weight mesh 2. So let's not do that, let's update it. Weight, yeah, just spell it correctly. I'll just repeat this. Okay. So weight mesh 2, and the same way, this is what we repeated by for each input we have an output, right? We have all the outputs mapped to one input, and for each of the inputs for each of the inputs. So our first accessor is going to be the input, which is the hidden layer. So it's going to be index j, index I, just the same way we did here, and then multiply this by neural net dot hidden layer index I. So now we know that we have already updated the hidden layer, so it's no longer empty again. It's no longer empty. Already updated with values in this above function, so we can now access those values and now pass it to the forward to the output neurons. Okay, and next we add the bias of the outputs, which you can say net value sum, net value sum plus equal to bias of output layer index I, and then as we assign the neural net dot output layer index I, which you can just say index 0 because there's only one output neuron, but let's just keep it professional like this. Professional, yes. Should not be equal to, we'll be using sigmoid again, sigmoid, and just passing the value into it, net value sum. Good. And remember our sigmoid function takes in a value n, it does this mathematical formula on it and returns the value of whatever this returns. Okay, this is the nonlinearity function. These functions add nonlinearity to our neural network. Okay, okay, we're making progress. So, and just like that, we are done with feed forward. Now, we're going to another interesting part again. Which before we go to the back propagation and then the actual. Okay, okay. So now we're done with feed forward, but we're done with everything that has to do with moving like this, moving forward. We're done with that. So next thing now is moving backwards. Now this is the actual training. You want to train this neural network, like actually training. This is where it learns. If we don't do this, if we don't do this, carry out this process, it's not going to learn actually. Okay, so we want to learn, and that's what we're going to take up and carry out this next process, which is actually going to train the neural network. So that means we're going to compute the error. As I said in the previous video, compute the error for each of these neurons, this neuron, this neuron, this neuron. Compute the error for each of them, and that's what we're going to update the weights that are connected to them. Okay, so we have to first compute the error for each of them, and then use that error to update the weights. Remember, we're updating. The only thing we're changing is just the weights. That's it. These are the only things we're going to be changing. Okay. Now, I just thought about it. Now I thought about something. This is not C++. In C++, I could just do a back propagation. I probably just pass these values by reference, so I can update them directly inside the function. But that's not actually how JavaScript works. It's not the same thing. It's not the same way. So why don't we define these guys as a global variable, so we can just update them directly? Okay, it doesn't change anything actually. So const, okay, even this like this. So, this should be equal to an array, remember to the array, equal to an array one. Oops. Alright, and this is it. Good. Okay, this didn't change anything. Remember we saw when we outputted the weight mesh, it's just like a matrix, right? So it could hold multiple values. This is the main array. You can hold a bunch of smaller arrays, and this bunch of smaller arrays now hold numbers. Okay, straightforward. Okay, alright. So that way we'll be able to access it globally and update it globally without having to worry about passing like that. So we just basically have passing here. Okay, let's just also do the same thing for these guys. Okay, for this bias, make it then. Don't worry, when we get to the main function, because this is just what just creating templates we're going to use in the main function. So you see how we're going to use check these guys. So same thing here, but this one is just going to be a single array. They are just single arrays because they do not represent any form of mapping. They just represent a single hidden layer which just holds a couple of neurons. So it just holds values for each of these neurons. Just a single array. Alright, so for our feed forward, the only thing we have to now pass is the order. That's all. Okay, let's now write the next function. So, as I said, we have to calculate the error of each of the layers, of each of the each of the output neurons. Let's calculate how well did they perform. That's where we kind of like query our neural network. Okay, what did you print out for me? You probably print out 0.9. But the actual answer is supposed to be 0, right? So you're wrong. So we now penalize it. So that's actually where we now do the actual error calculation. So when we're using mean absolute error here, there are a lot of error metrics. We have categorical cross entropy, we have binary cross entropy, we have mean squared error. And based on my own research, I think mean squared error is actually most suitable when you're dealing with batch size. Like when you kind of like when you're training, you kind of like check your inputs in batches. You don't train them, you don't like update the error like individually, you just update it as a batch. Sorry, as a size, as a batch, yes. Well, we're not getting into that here. But I believe if you have used neural network before or you trained the model before, you should probably know what I'm talking about. Okay. Okay. Let's continue. So we have to compute the error for each of these guys. Okay, so this is a function. This particular function here is a function that just when you call the function, you just have to pass in the order just said. So I don't know, let me just bring this one down. So for each of these training epoch, remember I said we're going to look through the training order. I know the particular order was supposed to use for the neural network, right? That's the same order we're going to now use as well to calculate, okay, which neuron are we at? Okay, which training sample are we training currently? Is it the best training sample? That's how we can now get, okay, for that training sample, let's get the actual value of the output and then compare it. And this video is going to take too long because I'm trying to explain exactly how everything works. I'm trying to explain how everything works. I'll just I'll shorten it. I'll divide it into 2 sections, I believe. Okay. So here, maybe I should just stop here. This is getting long. Well, let's just continue. Don't worry. Let's just continue. So let's calculate the error of each of the output neuron. So how we're going to do that is it's going to return a function for us. The function is going to return an array, which is like just like if we have, for example, now if we have multiple output neurons, right? Then this function is going to return an array of all as per all those output neurons. But since we have only one output neuron in this case, the array is going to be returned by this function we're going to create now. Compute. It's going to just have one single element, one single number inside. So return output neuron error. Okay, so remember we're going to pass in the order to know the exact training order we're dealing with. Okay, and we can just create an array, const return array, just give it a name like this. So we don't forget, just say return array. Okay, now we just have to run some operations here. So since we already have the training order, we're just going to look through the outputs we have the neural network. In this case, as I said, we have only one output neuron, but this is just I'm not good at words, but okay, but this is just like to cover any case scenario in case we have multiple output neurons. Okay, so we're going to look through it. So create a for loop. We need the indexing. So we just say let I equal 0, I is going to less than neural net dot output layer dot length. We're getting the length of it. Here we're getting the size. It's kind of same thing, getting size. So it's the same thing, JavaScript equivalent. And I should increment. And then next we want to now do create a number. Let error should be equal to, now I'm gonna say now the output data. Remember the actual minus the predicted, and that's error. Gives us the error. Actual minus predicted. I will now pass it through the derivative of the sigmoid function, because remember when we actually forward propagating, we passed it through the activation function sigmoid. So we're going to pass it through the derivative of the activation function. So here we can say training output data index at the particular order, right? Index I, okay, just index 0, but no problem since I have only 1, minus neural net dot output layer index I, since you use the value here, and then multiply that by the derivative of sigmoid, just passing the content, the value of the output neuron into the derivative of sigmoid. Okay, this is chain rule differentiation in sigmoid. I'm not going to explain chain rule differentiation here. You can go back to your books. Well, in case you want to test it, you can actually pick out each of those formula and try to find the derivative of it. It's going to give you something similar to this what we're doing now. So pass it through derivative. I'm going to pass in here this value here. Okay, and this should give us the error for output layer. And then lastly, we're going to now say return array dot push into its error. Okay, good. Now we've calculated the error for this neuron. Now the next thing we have to do is calculate the error for each of these guys now, each of the hidden layer. Let's get the errors as well, because the error that we calculated for this neuron can only be used to update this weight here. It can't be used to update this one, because the weight must be updated by the error of the neuron that they are connected to. Okay, that's actually how it starts. That's the rule of chain rule differentiation. That's how the magic goes. Okay, so therefore I'm going to come here. Now we have to calculate the error for each of the hidden layers. We'll now go to the actual backpropagation function, and then we'll be done. Yeah, we'll be done. That will be it, and I can now test it. Okay, so let's create this function. Function compute hidden layer error. And what do we need? Okay, we just need the output error. We need the output error. Okay, I actually mentioned this, but for us to be able to calculate the error of these two guys, we need the error of this guy. Okay, I'm going to see how we do it. So that's why most people won't actually go into creating a neural network for themselves by themselves, because it's kind of complicated, and you know what's actually much more hard. What more hard is actually when you're doing your research to create a neural network. The information is kind of scarce and can be confusing. Most people won't create it; they'll just explain it for you. Okay, but the advantage you're getting here is you learn to create it. Okay, so now we just have to pass. Remember, we declare these guys as global variables in our JavaScript, so we don't have to pass them to the function. So we just need only this one first, like global variable. It's just a function that returns an array of errors. Okay. All right. Now let's see. Now the formula for calculating the error of the hidden layer, the hidden layers, yes, neurons of the hidden layer, with respect to the error of the output neuron. Error of the neurons of the output layer, yes. Calculate the error of the hidden layer with respect to the error of the output layer. Let's put it like that. So first thing we're going to loop. Let's explain. We're going to loop into the hidden layer for each of the neurons in the hidden layer. What calculate the error for each of them. So we're now loop through the for each of the outputs. Each of the output error, which represents the errors from the output layers. So we're looking through each of the output layers and then getting their errors. But in this case, we really have the errors as an array. Remember here, we created this is going to be the function that creates this output error. Okay, so our mapping it based on sequentially, based on the way the output neurons are actually stored in the output layer. So, and remember, each of the hidden layers connected to each of the output. There are two output layers here. This guy is going to connect to both of them, so we need to use both of them to replace his error because he's connected to both of them. Okay, that means that the function is just very simple. We just multiply the weight connecting it's actually very simple. What we just do, multiply the weights. This presents the weights, right? The weight connecting that hidden layer, that has hidden layer neuron, that's hidden layer. Okay, let me explain now. The weights connecting the two neurons and multiplied by the error of that particular neuron. Okay, let's go here and see. So we're saying to get the error of this guy, we have to sum. Remember, if there might be more than one neuron here, but since there's one, it's just the weight, this weight here connecting these two neurons is going to now be multiplied by the error of the neuron itself. Simple, right? The weights connecting both of them multiplied by the error. That's how you get the error of this guy with respect to this guy. Simple, straightforward. Okay, So, and then after I got to that error, you're going to pass it through the derivative of sigmoid. Okay. Okay, pass it through the derivative of sigmoid. Yes. Just like we're going back, right? As I said, back regression. So we're just transporting the error backwards. Remember before we were just doing this, whatever you have here times its weight is going to be whatever is going to be summed up here. But here in this case now we're using errors instead of the actual content of the neurons. So the error of this guy multiplied by the weights, right? That's going to pass it through the derivative. So instead of now passing it through this activation function here, we're just passing through the derivative of activation function. This is the concept of backpropagation. So it's very much similar to forward propagation, but a little bit just like we're negating everything. Okay. And okay, so let's build it. So first things first, look through each of the hidden layer neurons. For loop, let I equal to 0. I is going to be less than hidden neurons, and I should increment, and then create the next an error. So const, it's not just const error. Sorry, let error equal to 0, because we're going to be summing up the errors we get. But in this case, there's going to be only one. Or just in a safe, Jesus Christ. Okay, let's just continue. Just like to be on the safe scenario, we're just going to look through, assuming there might be more than one output neurons. So for loop, let j be equal to 0. J is going to be less than output neurons, and then j should increment, and then the error is now plus equal to, now as I said, the weight times the error of the output neuron multiplied by the derivative activation function of that particular hidden layer. In this case, we're using the activation function of sigmoid, so we're going to use the derivative of sigmoid. So when it comes to error, we are using the derivative of the activation function, not the activation function itself. That is the concept of chain multiplication. So the mathematical equation for all this is actually very complicated, and you might not understand it, but this is the practical implementation of it in code. Okay, as I said, I think I said in the last video that it's kind of complicated, but we're going to see how to implement the code. Alright, so here we're plussing them equal to, and then the weights now. Since we define as a global variable, we're going to say weight mesh. I'm doing weight mesh 2 because we're dealing with this weight mesh here, not this one. Okay, we're dealing with this one here, so we're using weight mesh 2. Okay, the weight mesh 2 for the inputs, mapping based on inputs, is going to be index I, index j, because the hidden layers are actually our inputs for the weight mesh. The weight mesh, the hidden layers are input, the output layers are output. So the inputs, they're followed by outputs. Okay, and then that value will be multiplied by the output. So okay, let's make it output error. Output error the length. It's still the same thing actually, since that's the exact same number, but let's just use the length so it makes it much more easier. So output layer, output error, like that. Yeah, index j. And yeah, that's it. So we're going to pass this through. Error should be equal to error multiplied by the derivative of the actual content of the hidden layer, and this is how you calculate the error. The sigmoid of neural net that's hidden layer, index I. Okay, and we're going to be returning this. So here we're going to create const hidden errors equal to new array. Let's call it so equal to this. And so we're just going to push into this the array here. So what we've also calculated the error for that particular hidden error. I'm going to push it into okay. It's just a one-dimensional array. So say hidden errors. Let's push. I'm going to push in error here. Okay. And lastly, we're going to now return hidden errors, and that is it. So the next thing is to move into our backpropagation code now. So this one is the one that actually updates the weights, updates them based on the errors that are calculated. Okay. And also updates, so we use the learning rate. Also updates the bias as well. Also done with that, let's now call them. So we're gonna start. So you see here, as I said earlier, we're gonna start instantiating all those weights. So the weight mesh one is going to be called the create weight mesh, and then we'll pass in so things we want to pass in. Okay. Alright, so let's pause this video here. Alright, let's create our backpropagation code. Alright, let's see now. So the backpropagation, so remember, I don't really need to look at C++, but this represents a parameter representing the first weight mesh. So remember, we've already in JavaScript, we already declared this as a public variable, so we don't have to pass it here again. Now the way of pass stage, we don't have to pass in any of these guys. The only thing we're going to pass in is just the order. Let's create a function. So the function back propagation, and then we pass in the order into it. Okay. Let's just check something. Okay, it's recording. I just confirm it's recording. Okay. So now, why did we create these functions? Now we're going to use them. Okay. So what we did now was this. We created these functions because we wanted them to return a value which we're going to be using. We needed these values. As I said, we need the errors of each of the neurons to actually update the weight. Backpropagation actually is meant to update the weight. That's the whole concept of it. That's the whole meaning to why we actually made backpropagation in the first place, to update these values, to adjust them, correct them. Okay, and trust me, this is the foundation of every AI you see, ChatGPT, any AI that you're going to ever see. This is exactly how the concept of their training works. They actually adjust their parameters, which are their weights. The only difference is that ChatGPT probably has a different structure than this. Okay, but all the same, this is exactly how the training works for AI. This is how AI is learned. Okay, now, so let's continue. So we're going to define our output error. So output error, remember I've already written a function which is, I said compute. This is compute. Okay, compute. Yeah, okay. So just we're going to run the compute output neuron error. So it needs just one thing, which is our order, which we are passing in here. And then the next one, which is compute, is hidden. Let's call it hidden errors. Hidden errors is actually going to pass in the compute hidden error, and the compute hidden error actually needs the error of the output, right? That's actually why we needed to do this one first. We'll now pass it into here. Okay. Good. Now we have our errors as arrays. Now we haven't actually called the backpropagation and feed forward, so we might not be able to test to see what they return, but we're going to do that soon. So now let's go to the part whereby we update the weights now. So for updating the weights, so first this is to update the layer 2 weights, right? So if you have to update, let's update it sequentially, or let's say sequentially, but since we're going backpropagation, we're going backwards, let's do this one then for this one. Okay, but we can do it any way you want. Actually, we've already gotten the errors, and that's all we needed. Okay, so now to update this one, each of these weights, and we have to get each of them. Alright, so remember, for each input we create all the outputs. Okay, weights connected to all the outputs. So if there are 2 outputs here, you're going to have 2 weights connected to the 2 outputs. So now let's look through them. So for looping into the you know, it's a two-dimensional array. So the first loop gives us the rows, right? Gives us the rows. I don't know if you understand here. Gives us the rows, right? I'm sure you understand. And then the second gives us each of the content inside each row. Okay, and that's actually that's the actual weight number, like the number we're looking for. So now to update the weight, we have to multiply the value of the previous of where it's coming from. Let's put like this. So update the weight, the function, the mathematical concept is this: multiply the value of where we're coming from times the value of where we are going to, no, times the error of where we are. Okay, it's like this. Sorry, the mathematical function is this: the value of where we're coming from, that's the neuron value, which is in this case for layer 2 is the hidden layer. Let's show the slide. So the neuron value of here multiplied by the error of here. Okay, so for this particular weight, we have to multiply the neuron value of its, let's just call it its input neuron, where it's coming from, multiplied by the error that we got from where it's going to, right? And then multiply by the learning rate. Learning rate is just a number to slow the learning down. We just multiply everything by 0.1, so 0.1 just reduces the number. Okay, that's the concept. It's very straightforward. The actual value of the neuron of where we're coming from multiplied by the error of the neuron that we are going to, then multiplied by the learning rate. Okay, let's just do that. It's straightforward. You can just call a for loop. Let I equal 0, I is going to be less than weight 2 dot length, I should increment, then call another for loop. Let j equal to 0, j is going to be less than weight 2 index 0 dot length, and j should increment, and okay, so with 2 index 0 dot length, so getting the actual size of the rows, the columns, the rows. So just imagine as a two-dimensional array, a matrix. Okay, now so this should not give us access to each of the weights. So way to actually update them, we're saying weight mesh 2 index I, index I, index j. So getting the actual weight itself now should now be equal to, should plus equal to. Now you might be wondering, most times we're actually trying to correct the neural network, right? So why didn't I just say minus equal to? I know most of the tutorials you probably check, they'll tell you it's minus equal to, right? But I'm going to explain why we're using the plus in this case. So let's get the neuron where it's coming from. So remember, this is the weight mesh 2, which is this. I don't know why I'm wasting so much time explaining, but this is the weight we're dealing with here. So I'm going to now call and say neural net dot hidden layer, which is the input of it. So the hidden layer, going to get index I. I want to get index I because this is the input. So remember, the input is always the first I value accessor, and then the output is the second. Okay, then multiplied by the output error. So remember, we'll calculate our output error. So I guess it's index j. Then multiplied by the learning rate. Learning rate. Sorry, I'm very good at typing fast. Anyways, now that's it. We have updated the weight of layer 2. It's actually that straightforward. So let's update the weight of layer 1. So the same principle. Let I be equal to 0, I is going to be less than weight mesh 1 dot length, then I should increment, and then we can say a for loop again. Let j equal to 0, j is going to be less than weight mesh 1 index 0 dot length, because I'm just getting the length of one of the rows, because all the rows actually have the same length. So and then j should increment, and then weight of this is weight mesh 1, index I, index j, index j should be equal to plus equal to, or trying to correct it, so should be plus equal to neural net dot input layer index I multiplied by, now we're now using the errors from the hidden neural errors. So hidden errors index j multiplied by our learning rate. Good, and that is it. Well, all of the weights. Now next, let's update bias. So the bias is, the updating bias is just simple. We just multiply the error of that neuron. So we're creating a bias for each of them. You just multiply the error of that neuron times learning rate. That's all. Just add it to I'm going to explain to you guys why we're actually adding it. Okay, so plus equal to that. It's just plus equal to it. So we're going to get for each of the hidden neurons, get it bias, and just the error of that hidden neuron, just add it, multiply the learning rate to the bias. Okay. Now we're going to do a for loop. Let's update the bias. So let I equal to 0, I is going to be less than bias mesh. Let's start with bias mesh 2. Let's spell this correctly. Okay, let's call it bias output layer, and then let's say I should increment. So remember, it's only one neuron here, so we have only one bias. So we're just going to say bias output layer index I should plus equal to the output error, which is for that corresponding output neuron, index I multiplied by our learning rate. Okay, and let's just copy this, paste it, just update. So for the update the bias of the hidden layer. Okay, so change this to bias hidden layer. This becomes the hidden errors. Good, and we're done with backpropagation. Easy peasy, right? It doesn't hurt. Now the next thing we want to now do is to start initializing our values, our parameters. So start instantiating them. Also, let's use the let to define this, because we're going to update it. We're still going to update the content of it. Let's use the let keyword. Okay. Yeah. Alright, so here, so let's call our training epoch. The training epoch just is where we kind of like we reshuffle the training order, then we now call it for loop to loop through each of the training order, and then call it fit hold and backpropagation and blah blah blah. Okay, so here just call a function training epoch, and then it doesn't actually need any parameters. Okay, so what it does first, it calls the reshuffle training order, right? And remember that we defined the training order as a global variable, so the reshuffle training order has direct access to the training order itself. Yeah, we have direct access, so we just have to call it like this. Next, we call the for loop. So I'll assume that we reshuffled it. So let's call it for each loop. So just say training order dot for each. So call feed forward, passing the order, which of course is val in this case. And then after that, we call a back propagation, passing the order as well, and that is it. Our training epoch is done. Next and final thing is for us to now our final function, which is where we call the main thing. So let's just say const start network. Start network should be equal to a function. Okay, so here what's not starting, so we don't actually need this. As I said, I told you that we didn't need this function, so let's just leave it. So let's start instantiating our layout, our weight mesh. Okay, so you see why I created those functions here. So the first one, weight mesh 1 will be equal to create layer weight mesh. So we just have to pass in an input and an output, right? So in this case, for the first weight mesh 1, our input is the input neurons, output is the hidden neurons. I mean, for this mesh, the input neurons are our inputs and the hidden layer neurons are our outputs. So this means that here we're going to pass in input neuron, and pass in our hidden neuron. Okay, now for weight mesh 2, it's going to be create a layer weight mesh, and then the passing. So our input now is our hidden neurons are our inputs, and our output neuron is our outputs. So I've just created the weight mesh. Now let's create a bias mesh. Okay, bias hidden layer is going to be equal to create bias mesh. Just needs one value. So in this case, it's the hidden. Let's create for the hidden neuron. Let's create bias output layer should be equal to create bias mesh for the output neuron. Okay, good. And finally, all you have to do is call our number of epochs and then call the training epochs and it's going to train and blah blah blah. And we're done. Okay. So now we're going to create a for loop. But before we do anything, let's try to print out all this weight mesh. Let's be sure that it's actually creating it correctly. The console.log weight mesh 1. So weight mesh 2. Console.log bias hidden layer, bias output layer. Okay. Now let's do Ctrl J and run this. Okay, and let's run. Okay, sorry, I didn't call this function. It's just called start network here. Okay, and let's run it. Be sure it's creating correctly. Oh my god. Okay, so we have an issue. Oh, I think I know why. I didn't add the return statement here, did I? I did, sorry. So let's return new. It's good to test it now. Okay, good. Alright. Something is still round. Why am I rounding? No, sorry. I shouldn't round this. I wasn't supposed to round this up. Sorry. Because we don't want it as an integer, we want it as a decimal. So okay, run. Okay, good. So this represents the first array we're having here, then the weight mesh. So let's do the reference to this. So this, let's assume we have 4 weights in this case: 1, 2, 3, and 4. This weight for this input neuron is this one. This weight is this number here. This weight is this number here, and then this weight is this number here. So this is our weight mesh. Good, understood. Alright, for the next weight mesh now, weight mesh 2, we have only 2 weights here, and that's why we have 1 weight per each for each of the neuron. This is just only one output layer. So this one represents this one, and this represents this. The bias mesh, this is bias mesh for hidden layer. There are only 2 hidden neurons, so we have 2 For output layer we have only one, so we have one. Good. Control J. Now let's continue. Now I'm going to train this in C++ first before we now train in JavaScript, and then we're going to see how many epochs it takes to train to then blah blah blah. Okay, and before we do that, let's call our epoch. So epoch just represents how many times you want it to call to train. So sometimes when you train too much, you overfit data. Well, we're not going into those things here because I just want to show you how to create neurons from scratch. And if you're interested, we can actually work together to make a much more advanced model, which I'm also working on right now. But I will not do the tutorial on that one because that one is way too complex to be made as a YouTube video. Okay, I'm not going to go into that one. Okay, but nevertheless, let us call our epoch. So for loop, let I equal 0, I is going to be less than, let's train it for 1000, I should increment. Okay, so inside here we just call our training epoch. Training epoch. Just call this function, so it's going to train itself. Okay, and here is where we now print out. We want to print out end results. Let me see. So we'll call it feed forward, and then we'll call it input 0 x1. Okay. So after training, we want to now see the results. So what we're just going to do is console log. So console log first. Let's use templates. Input 1. So input is training input index 0 to a space input training index 1, and then we're going to leave a space again and say actual. So the actual values we expected for them, the actual result for that output, actual output. I'm typing rubbish. Actual output is now going to be the actual, like the predicted output, what they actually predicted. So I'm going to be neural net dot output layer index 0, and the expected. Now what did we actually expect? The expected output is training output. I forgot something. This should be at that particular order, right? Yeah. So training output at the order index what? Index 0, because there's only one output. Okay, and of course we're going to be looping into the training order. Okay. So we just got for loop for each loop. So say training order, but for each. Please don't be confused. I'm just doing simple JavaScript operation here. Okay, so we'll just call this inside of here x. So there we go. Good. I don't know if we're going to do something like this. Just to make it order 0, 1, 2, 3. Could this work? I think it should work. Okay, so I've not tried it before. Okay, it actually works. So I'm just going to use the default order of 0, 1, 2, 3. Alright, so let's train it now. Now it's time for training. Well, first we're going to train it on C++ first. I'm going to see how it's actually trained, and then so this one is on the box here. So I'll be pausing this video when I want to train it because it needs CPU to train, and my system is not that powerful to hold a screen recorder and this kind of operation at the same time. So let us pause this video to train the results. Okay, so what we train it for 1000 epochs, right? 1000. I'm training in C++ and this is C++ code. So we train the 1000 epochs and give us this results, which is not good, right? This doesn't look good. But then what happens when we train it for an additional period of time? So now one concept about neural network is this: when you're training, there are a lot of parameters you can tune, but this our simple neural network doesn't have all those parameters. Those parameters involve normalization. You have to normalize the inputs, a lot of other things we have to implement, right? A lot of other things like fine-tuning and other things to just tweak to make it train faster. But this is just a raw example. Most likely it's going to take a longer period of time to train. So let's make it 10,000 iterations, okay? And I'm going to pause the video. As I said, we'll pause the video. So let's just create that one. So we're going to train it. So then pause the video. Alright, so we just unpause the video. Did I unpause it? Yes. So we've unpaused the video and this is our result now after training for 10,000 epochs. So you see it actually that one give us a very good result here. So the actual output was 0.0 here, and then what we expected was 0, and it's close, right? The actual here was 0.932 and we expected 1, which is correct. The actual here was 0.07 something, we expected 0, it's on track, and this is 0.92 and expected 1. It's good. So if we keep on training it, increasing the epochs to 100,000, it's only going to get better, right? But this is not advisable actually. Training for a longer period of time is not advisable. Once you've gotten a good result, because usually you have error metrics or accuracy. Once you see very good accuracy, you don't need to go further. But let's just see what happens if you keep training more. Okay, there we go. I said this is CPU intensive, which will take time. See sometimes difficult to print out the results. But this is what we're seeing here, right? So this is the outcome. So let's now test with the JavaScript version that we just created. Okay, let's test with JavaScript version. So here, I'm just going to come here and run this on node to export.js. So I'm going to pause the video. Okay, so I kind of made a mistake somewhere. So it tells I is not defined line 54. So if you look at this code that we wrote here, we're actually did a loop here. I don't know if someone saw this from the beginning, and I'm so sorry. But let's address this now. So we actually had to loop in, but now in this case we actually doing a backward loop. So I'm sure, let me explain what exactly this means. So if I was to write a JavaScript version of this, it was going to be that the for loop is the backward loop. Let I be equal to training order plus length minus 1. Now why are we saying length minus 1? Because when it comes to indexing, I'm sure most of you know, if an array has 4 elements, its length is 4, but the maximum index is actually 3, right? So we don't want an equation whereby we're having, because it's going to start from 4. If it starts from 4 and then the maximum is 3, it's going to give us an error. We have to negate it by 1 minus 1 for me, so it starts from 3 or 1 minus 1, okay, something like that. So you're just going to leave 1 out because programming does with 0 indexing. Okay, let's just wrap things up. And then waste now decrement. Sorry, say as long as I is greater than or equal to 0. Okay, that's our condition. And then I should decrement. And that's how we're going to get our I, because it tells me I is not defined here. Paste this here. Good. Alright, so let's run again. Let's run our program. Let's hope it works this time. I did not save this. Okay, training data ap.h line 93. We have some bugs. Got the feed forward. uh, saying here that now we provide to undefined even for each. Alright. So I should just pause this video and do this debugging, but let's just keep it going so everyone can learn. So let's see, it's printing out values for us, but it's gonna print undefined at some point. You can print undefined. Guys, yeah, so I did some debugging on the code, and why it was giving us that undefined was because from here we added, remember we added the +1 here. Now this was going to go to an error because this function returns a random number between 0 and I. When I say I plus 1 here, it means that when I is actually like 3, I plus 1 gives us 4, right? So it gives a random number between 0 and 4. So imagine that gives us 4. 4 is not part of the index. So the index is 0, 1, 2, 3. That's why we didn't have to put a 1 here. We just leave it as I. And here is actually a different operation. We're using a modulus operation here to get the random number, right? Because this returns a high random, like a high value, random high value. So we just use this to get the modulus. But this is a whole different implementation. So here's also a different implementation as well. Okay, so and another place I saw another issue was just check here, we didn't put a dot length here, so you have to put the length because this is an array, so you have to put the length, and that's it. so let's test it. Remember we've tested for the we've tested for the C++ code, and C++ code actually works. Let's try it again. So this is for C++. So we're training it under 300 epochs. We're using the ReLU activation function. Let's see. Feed forward. Yeah, we're using ReLU activation function, and this is the feedback. So for an expected 1 and give us 0.96, expected 0 give us 0.02, expected 0 give us 0.03, expected 1 give us 0.96, and that is correct. That is good. So now let's see what happens when we actually do with JavaScript. So I thought this was a bug initially because we actually literally just interpreted the entire code from here to here, but then let's see the difference between using a low-level programming language like C++ to build a neural network and using a high interpreted programming language like JavaScript. Okay, so if we were to run this for JavaScript now, not Xor, let's check some parameters to be sure things are set. Let's increase the learning rate to something like this. I think we're using ReLU for the activation function. Yeah, we're using ReLU. Okay, use Sigma, but let's just try ReLU. We're on 10,000 epochs. So let's see the feedback. Okay, this is bad, really bad. Oh, I'm coming. This was using ReLU. Let's increase the learning rates. Now, you should know that this is the exact same code but in different programming language. You can see the difference in their behavior. Difference in their behavior. So difference in their behavior. This one is not actually learning as to when compared to the C++ version of it, which is this. Perfectly trains and learns, but the JavaScript version doesn't actually train. But this doesn't mean that our neural network is not working. It's just that it's how do I put it now? Okay, I actually did my research to see, okay, why is this actually happening? Because this is the exact same code we just interpreted from here to here, but then it's behaving differently. And the response I got was that this could be as a result of the precision in the calculation. So when it comes to numerical calculation, C++ has a much more does this calculation at a higher precision than JavaScript. You can actually tell from that by looking at let's just looking at these values, but you can see that the output, the way JavaScript actually brings out. It brings out in floating numbers, right? But C++ actually does some sort of approximation. So even if I can't really say for sure what exactly is wrong, but I know that this kind of plays a role. The fact, the way they bring out their like numbers, the way they present numbers and do numerical calculation is not actually the same thing. So that most likely is the reason why you can see difference in behavior. But this doesn't mean that the JavaScript code is not working. It's actually working, but it's going to work for simpler case, right? But for the XOR, you can't actually learn the XOR. Probably the only way it can actually learn is probably want to do some optimization, like normalize the input and output, then or scale it to a different scale, a smaller scale, a different scale, then it can work. So let's test a simpler illustration. So let's just do the AND operation. Okay, AND is this is going to be 0 0 0 and this is 1. So this is AND, right? So let's test for the AND operation and see if it's going to train. Sorry, okay, this is C++. Sorry, let's test for JavaScript. And okay, so give us this response. You can run it again. Okay, so if from here you can see that from its response, this guy actually is kind of having a higher value, like it's having a, because we expected it to be 1, the rest to be 0, right? So it's kind of like taking precision. Let's see what happens if we increase the learning rate, increase the rate. Let's see the output now. Okay, alright, so you can see from here it has trained and learned. So the reason why we're seeing things like this is probably because for every time that you in JavaScript, every time that you load you call on a new random number, it can like generate a totally random number for you, which can be like of any value or scale. So for the fact that it's generating random weights when you initialize it, that means that each initialization will take different amount of time to train, because the weights are just randomly decided. So the time for conversion and the number of epochs for convergence, I mean, is going to be definitely different, since they are all the weights. Each initialization is actually different. Okay, but one advantage with C++ is that each initialization of your weight is actually the same thing, although it's randomly picked, but whenever you initialize, it's actually the same thing. So it's always going to give you the same result, which makes it kind of more stable. So from here you can see that it can actually train on a much more easier task when we give it. This AND is like a linear task. It's not a non-linear task like it's not non-linear like XOR. XOR is a non-linear task. Okay, so you can see that in most cases it's actually predicting correctly, and I believe if we are to let it run on more epoch, then we should consistently have a very good result. Let's just say 50,000. Let's just test on 50,000, and there we go. So it probably should give us a little bit more consistency with outputs, something like that. So these are very low numbers. So from here you can see the difference between using it in C++ and JavaScript. The difference in creating the neural network in C++ and JavaScript. In C++, you kind of have more stable response, right? You can try to model the same stuff in C++ and get a very good response. Let's just try it. The AND operation, so just change this one to 0, this one to 0, and this one to 1. Let's try to model it in C++. Okay, let's just close everything. Okay, yeah, good. So it's perfect. So where we expected 1, it gave us exactly 1, and here this is 8 times 5, 8.5 times 10 raised by minus 10, which is a very low number. We can, so this means that it's actually even converting at an earlier point. So we can just reduce this to like 50. Let's see how it's going to do when we treat the 50 epochs alone. And you see, it's already giving us a very good response, 0.89. So this alone can actually decide from here. Okay, yes, the neural network has already learned. Okay, and see, just took us only 50 epoch, unlike JavaScript, which is taking us about 50,000. It's like C++ was actually 1,000 times better JavaScript in terms of machine learning algorithms. So this is what I said I was going to show you guys about the difference in using a low-level programming language like C and then an interpreted programming language like JavaScript for making your neural networks. So I think this will come to the end of this video. So in the next video, we're going to be I've created an advanced machine learning algorithm and library, which is much more advanced than any of these, and it's in C++. So we're going to be testing classification, regression, and some other neural network based operations. Okay, and yeah, so thank you for your time and see you in the next video. Don't forget to like and subscribe. Thank you.